Hello everyone. This project is on explainable machine learning, the visualization of training processes of deep learning techniques. The issue with neural networks and deep learning is that convolutional neural nets, which have been used for various reasons such as image recognition, language processing, speech classification, etc., are not very well understood. They are black boxes in essence. We have mathematical understanding of how they work and their convergence properties, but we don't know why they converge the way they do on any problem. As such, this does not generalize to theoretical robustness because we don't have computational information. So we would like to use visualization to observe the training process of these networks, to see what they're learning at each epoch, to determine some type of form and function of each layer by looking at these specific visualizations. Uh, One approach we take is viewing activation maximizers. So we take the features of each layer, the kernels, and we figure out what activates that kernel the most. This gives us a general idea of what that kernel might be looking for. So in our experiment, we built 6 models for the CIFAR 10 dataset. So the first model is presented here. It is composed of 3 by 3 kernels here. 3 by 3 kernels, all of them 32 kernel depth, the first two, and then 64 kernel depth for the next two, 128 kernel depth for the next. The tail component simply converts the convolutional output at the max pooling into a dense output that can then be fed out to the softmax classification layer. So CFAR2 is similar, just a higher depth, 64 instead of 32, 128 instead of 64, and 256 instead of 128. This is CFAR 3 and 4. So CFAR 3 is increases the field of view from 3 by 3 to 5 by 5 to 7 by 7. CFAR 4 reduces it from 7 by 7 to 5 by 5 to 3 by 3. Finally, CFAR 5 just slightly adjusts the depth values, 3264, then 64 128, then 128 256 between the max pooling. And CFAR 6 is just a deeper layer composed of only 32 kernels. So we validated these results. CFAR 1 performs quite well at 79% validation accuracy on the CFAR dataset. CFAR 2 has an 81% accuracy. CFAR 3 has 76% accuracy. CFAR 4 has a 10% accuracy. Again, it did not perform well, and we suspect it is because of the field of view that was quite large in the beginning and then got reduced. CFAR 5 has a 78% accuracy. CFAR 6 has only a 68% accuracy. We suspect it's because of the absence of residuals in the deeper network. So how do we perform this visualization? We perform gradient ascent with regularization. For each network, we start with sort of like a center image, so a grayscale image. We pass it through the network until we get to the layer that we desire and the kernel that we desire. Then we find the loss of that kernel, which in this case would be the activation. And again, we want to maximize activation. So we find the activation and then we consider that the loss. Then we perform gradient ascent. This is similar to gradient descent, except in gradient descent, we're trying to minimize loss. Here, we try to maximize the activation. And we find the gradient of the image with respect to that activation value and change the image with some regularizations to make the images more natural, including blur, decay, and pixel clipping. So here's a brief look at convergence. So we start with the random image, and then as it goes through several iterations, which are user decided, and in this case 150, we arrive at what the kernel is, what type of image would activate that specific kernel. So this is another. So this looks like the image, the blue color is the activator. And in this case, it looks like some type of texture information is the activator. We can note that in the middle, there was orientation information right here, and then it went to vertical. So gradient ascent is an expensive process because this involves pseudo training the model and for each kernel. So to speed it up, through TensorFlow at least, we must rebuild the computation graph at each time when we perform gradient descent. A way to speed this up is to build the computation graph in the very beginning and simply then continue reusing that computation graph for each gradient calculation for each model, for each epoch in that specific model type. So since we're using the Keras front end, the work seems to be slightly easier. We generate the loss here by taking the mean of the model. Then for each kernel, we append the gradient of that kernel, and then we regularize that, or rather we normalize that gradient, and we store that as a single computation graph that we no longer have to recreate. This simple step actually improves the time significantly. So here we can look at the results of regularization. These are some results from before regularization, and after we see that they are much more interesting. Rather, there it's easier to visualize what's going on. It's easier to see more details. So this is a website where some of the filters are stored as long as the website is up, and I ask you to take a look at them to view them. And again, some filters, some cases, the site doesn't work. So we can see this filter right here is storing some type of orientation information. This filter, perhaps patch or texture. And this filter is definitely storing some sort of texture information. We can see similar orientation information being stored in filters here. Now we noted that each image has kernel that maximizes it. So when an image goes through, some kernels will maximally activate and others won't. And it would be useful to figure out which kernels do activate an image in order to perhaps build a substructure. So we, in the CFAR, we list this information. We find that for the dog class, on average, the top kernels in convolutional layer 1 are, for example, kernel 27, 11, 8, 9, and 15, etc. And as it goes with the other kernels, other layers. So we wonder if we can combine this information to create a minified network. So we also note that there's kernel proximity for objects that are related. So horse and deer can be considered somewhat related, and we can see convolutional layers 4 and 5 have similar numbered kernels, and because kernels deal with relational or information, it is suspected that proximal kernels might store similar information. We know that automobile has a completely different kernel set for the same layers. So by substructure, we mean that, well, let's take this original network, similar to our CFAR1, and suppose we note that the red layers are maximally activated for a specific class. Then would it be possible to extract other red layers only and use them to build a new network and perhaps have it converge faster? However, we attempted a naive approach, and this seems to fail. Precisely because we built a feed-forward, we approached it from a feed-forward perspective. We simply took the kernels from start to end, the convolutional kernels that have the highest weight, highest activations, kept their weight, and set everything else to 0. Clearly, this still propagates redundant values to the network, and as such, we have high misclassification rates. I believe a new approach, a better approach, would definitely be working backwards. We look at the softmax output, find out which kernel, or rather which component of the softmax output is activated most on average by dog, and from there work backwards to see which weights affect that the most, which weights have the um, highest value connecting to that specific component, and from there again work back to the convolutional layers and build up a list of convolutional kernel maximizers. Another approach could be to only use the weights we desire, and instead of setting everything else to 0, get rid of everything else. This might prevent unnecessary computation and make the network lighter rather than as heavy for this task. So that would be my future approach, and again, all the code is at my GitHub. Thank you.